Welcome to this video. My name is Mark Scythian, and in this particular lecture we are going to cover the principle of insulation R value versus its U value. So that is the foam insulation for housing or other structures insulation. And so we have the R value of, let's say, 20 for a certain foam insulation panel, including its thickness. So that R value produces a U value equal to its inverse, or its reciprocal, with respect to watts per square meter. So I'll explain what the 0.05 watts per meter or R value of 20 means. So assume you have a structure, and we'll just take one panel. We have our dimensions here. And so there is 6 panels for a 15 by 10 or 150 square foot room or area. So we'll just isolate a certain square footage, and then we have to take it to the volume of the room. So if we take 12 by 15, 12 by 15, 2 of those, 10 by 12, 2 of those, and then the 10 by 15, 2 of those. We have a total square footage of insulation panel area of 900 square feet. So we can simply get the square root of 900 square feet. So that's 30 feet linear by 30 feet linear. So if we take 30 feet and divide it into 3.28, the number of feet to a meter, we get 9.15 meters linear. And then we cube that value, so that is a total square meters of 765.14 square meters of insulation area, 6 panels. We simply then multiply the 1/20ths, or 0.05 watts per square meter, times 765.14. We see that the square meters cancels out, factor label method, and so that's a 38 watts of continuous heat requirement to stabilize or keep the internal air temperature constant. So whatever temperature is selected, it will lose 38 watts of heat. So 38 watts of heat input is required. So that is based on dividing 38 watts into the number of BTUs per second per watt. So that's 1056 watts per 1 BTU per second. So 2 wattage values. And so that's a continuous BTU per second of 0.036 BTUs per second. So if we take the price of natural gas, that is at $2.90 per therm, or 100,000 BTUs. And then electric would be 16 cents per kilowatt hour. And these are average values or price metrics in the US in 2024. So if we took 100,000 BTUs, heat, per therm, and then we have a heat transfer efficiency for most natural gas furnaces of 80%. So 1 / divided into 0.8 times 0.036 times 3,600 seconds to an hour times 24 hours. That translates to 3888 BTUs per day, 450 square feet. So that's comes to 11 cents per 150 square feet, so per day. So before we move on to the electric, we can calculate let's say a 3,000 square foot house divided by 150. Then times 11 cents. So we're assuming these panels are sealed and well insulated. So we got 11 cents per day per 150 square feet. So that's $2.02 per day. Heating cost for a 3,000 square foot house. Under natural gas heating. Now we can compare it to the electric heat, and so that is to stabilize a air volume. So we have a certain air volume, in this case it's 15 feet by 10 feet by 12 feet. So it's 1,800 cubic feet of air at some density, pounds per cubic foot. So then we get pounds of air, and we want to hold that quantity or that volume of air at a constant temperature using our 20 insulation, 6 panels covering an area of 150 square feet. So just like it takes 1 BTU to raise the temperature of 1 pound of water by 1 degree Fahrenheit, when we're dealing with air, it takes 0.24 BTUs to raise 1 pound mass air by 1 degree Fahrenheit. So we'll just focus on the square footage. So that's 150 square feet. And we did an isolated analysis over 150 square feet, and then 3,000 divided into 150 is 20 150 square foot sections times 11 cents. So we kind of narrowed it down to about $2.20 per day. Natural gas heating, 3,000 square feet house. And that's based on this 38 watts of continuous heat at our value of 20 or a U value of 1/20th watts per square meter. So now if we clear up all this, and just focus on the electric cost using R20 insulation panels, 6 per 150 square feet, we can compare this to the electric heating cost. And again, of course, we're trying to stabilize the air volume as it has a density. So if, let's say, the air density was 0.068 pounds per cubic foot times 1,800 cubic feet, that's 122.4 pounds of air mass in a 10 by 15 by 12 area, let's say room or area. So like length 15 feet, width 10 feet, and height to ceiling 12 feet. So that's 1,800 cubic feet. And then let's say the air density is 0.068 pounds per cubic foot. That translates to 122.4 pounds of air that we have to stabilize and keep at a constant temperature using our value of 20. So this means 1/20th watts per square meter of insulation area has to continuously be delivered. So it's, not significant, but it does boil down to 38 over 1056 or 0.036 BTU per second. And we know that there is actually 24,800 BTUs per pound of natural gas, but it's also rated at $2.90 per 100,000 BTUs, or 1 therm. So we got that at $2.20 a day. So now if we just take the same thing, 38 watts per 1,000, and multiply that times 24 hours, this becomes 38 over 1,000, so 0.038 times 24. So that's 0.912 kilowatt hours. And then we multiply that times 16 cents. For 0.145, so 0.15. So that's 15 cents per 150 square feet. So 3,000 divided into 150, 20 times 0.15. So this comes to $3 a day for a 3,000 square foot house under the AC electric model. So figuring out if it's the watts electric heating, like a 2,000 watt heater, or when it comes on or off, or if it's an analog thermostat, or if it's graduated, it all culminates to this 38 average watts per second, or watts are over time, so that culminates to 0.036 BTUs per second of heat, or 38 watts continuously, and that includes the off and on times, but it's the average value. So then we can conclude that at a pretty good insulation, we'll just call that 20 or higher, everything becomes relative thereafter. We have $3 over 220 so that is 36.3, so it's 36% more expensive to use electric heating. That's because of the cost of the natural gas and the electric, and it's more than just the natural gas and the electricity, it's also the infrastructure and how the cost of natural gas has increased. But of course, electric will always be more expensive. Depending what kind of natural gas furnace you have, it might be really expensive to set up, but after everything pays itself off, then we tend to think, or traditionally, the cost of natural gas was considerably less than electric. If we look on the other end, 2.2 divided by 3, we have 0.73, so 27% less expensive to go on the natural gas end. So approximately average median of 30% more expensive to use electric heat versus natural gas. But traditionally, the cost of natural gas was as much as 50% less expensive, but the cost of the infrastructure of natural gas has considerably risen over the last decade. So this lecture was originally focusing on the R value. However, the practicality of such a lecture is to equate this to the heating costs, either gas or electric. So with opening doors and all that stuff, we can ascertain that we have between a 30 to 36% more expensive heating cost with electric versus gas, and that kind of includes opening doors and all the other normal losses. So overall it could be between 30 and 40% more expensive to use electricity. But the main takeaway of this lecture is the R value is simply the U value in inverse. So in this case, we can isolate the information in simplicity that when you get an R value for insulation, just find its reciprocal, and that becomes the watts per square meter continual heat requirement multiplied times the total insulation area, all 6 sides, or I would figure the floor insulation could be a major factor in heat loss, so we'll just say it's 6 sides insulated. And there's different floor and wall sections, schedules, etc. But we could have, we always have higher energy moving to lower energy, second law of thermodynamics. So in a winter environment for sure, or a colder environment, heat loss through the floor is a major consideration. So without an assumption, it is a 6-sided insulation containment. And by taking something like 150 square feet or something much smaller, we can scale it to a larger value. So a well-insulated interior, such as a R20 insulation, will require 0.05 or 1/20 watts per square meter of insulation area continuous in the form of heat in order to keep a constant air temperature or volume of air temperature. And the practicality is doing so electric heat will cost around 36% more than natural gas to do so. Thank you for watching this lecture and have a great day.